Computer Science in the School of IT and Electrical Engineering at University of Queensland. Prior to joining UQ, Archie was Research Fellow in Smart Grids at the University of Sydney from 2011 to 2019, and a postdoc fellow at the University of Southampton 2009 to 2010, where he completed his PhD as well. Archie develops and applies principled artificial intelligence. I actually don't know what principled artificial intelligence is, but maybe we will get a better idea about it. Game theory, optimization, and machine learning methods to solve large scale and dynamic allocation, scheduling, and queuing problems. His recent research has focused on applications of these techniques to problems in future power systems, such as distributed energy resources, to provide power network and system services. Please join me welcoming Archie.
Thanks, Ali, and to the other presenters. I don't think any of them are here today. They did an excellent job in laying the groundwork. There's a joke that goes around the AI community that AI is the stuff that doesn't work yet, and if it works, it becomes maths or engineering or something like that. So things that were AI 20 years ago are now sort of standard practice. So today I'll be going over, first of all, clustering and then classification methods, and looking at a couple of key applications of these two classes of problems or techniques to some sort of highly relevant issues in power systems, mainly to do with modelling loads or modelling things like networks. So, wrong way. Let's get the hang of this. So I'm going to just jump straight in and get into this without too much motivation, because I think we've covered a bit of the motivation for these methods over the last few days. So in general, clustering and classification are both pattern recognition problems or tasks. The idea is to look at some data and try and work out what's going on within the data. Okay? They both involve assigning an output value, a label, usually, to a data object, given a set of input values. Okay? And the set of input values is something which is somewhat flexible. You can choose what input values you use. You can choose transformations of raw data, combinations of different things. There's quite a bit of flexibility there. And an awful lot of the research that goes on in both clustering and classification methods has to do with this, choosing the set of inputs. It's called feature selection. I'm sure you've heard the name before. Clustering and classification are often mixed up, but they are distinct areas of machine learning. Clustering is an exploratory data tool where you don't have labels. So in that sense, it's unsupervised. There's no training labels available to you when you're doing your exploratory data analysis. You're just looking at things and trying to work out how they might be grouped or arranged, or ways that you can sensibly organise the data in order to make some deeper insights into what's going on in the system in question. Classification, on the other hand, is a supervised learning problem where you have training labels. So you have both the X's, the inputs, and the Y's, the outputs. And the task is to find a mapping from the inputs to the outputs, or the features to the class labels. So classification is grounded in some more principled backgrounds to do with statistical inference. So most classification methods, most of the ones that I'm interested in anyway, grow out of the statistics literature and are backed up by some solid mathematics. There are also heuristics and various other things which work quite effectively, but they aren't the things that I'll be focusing on too much today. The other aspect of classification is you can use, once you have a classifier, that's the model, the mapping from inputs to outputs, you can use this to predict future values based on inputs of things that you haven't actually observed the output for yet. So in that sense, it becomes a predictive tool as well. So it's really quite useful. And Spiros was talking earlier in the week on using classifiers to predict stability criteria in power systems, okay, rather than waiting for the system either to be perturbed by some sort of problem or emergency, or running very computationally intensive time domain simulations. You might be able to use a classifier to do prediction for you. Okay, I'll get this right eventually. Going forward is down. So clustering. Let's do some thinking. Imagine you're an engineer at a DNSP. That might not be too hard for a few of you in the room. You're tasked to work out how you can use customer data, so metadata, that you've bought from a startup that's doing something like solar analytics or reposit power, okay, where they're collecting behind the meter data, sub-circuit data, voltage measurements, a whole lot of other things that the nasty retailers won't give you for free. And you're particularly interested in the problem of phase identification because your networks were built a long time ago and you don't know what phase an awful lot of your customers are connected to. Okay, this is a very real-world problem. You have customer data which is time series. It's collected at some sort of resolution. There's a number of different fields which are collected. This is something which isn't really standardised across the country, but you have access to some of this data. What do you do? How do you go about analysing this data? Have a think. I'll give you 6 traces to give you an idea of what it is you're looking at. Okay, so these are voltages across a number of days. I think they're at 3-hourly peak voltages. What would you do with this data? What could you do with this data? Yeah, given we're in a session on clustering, you'd probably try to cluster it, right? So what does clustering involve?
Finding similar behaviors.
Yeah.
And correlating them in groups that are similar.
Yeah.
Not similar.
Exactly. So finding similarities in the data. Right, the task is to group different data objects, which in this case are the time series. Group them according to their similarity. Okay, so what's the similarity of a time series? How do you measure the similarity between 2 time series?
Correlation between them?
Yeah, that's one way you can do it. Correlation. But there are other ways. So there's a whole range of other ways. And this goes to the idea of feature selection. For the voltage data, because the voltages on a network, you know this with the physics of the network, the voltages on the network are coupled fairly tightly along a feeder. Okay, so you'd expect the correlations to be fairly significant, and that can be very useful. For other time series, so if you're looking at customer load data, for example, the correlations are nothing like that. Just because John down the street has got home from work early and turned on the oven because he's cooking a roast tonight doesn't mean you're doing anything different. But you both might be cooking dinner using your electric appliances between the period 4 p.m. to 6:30 p.m. Okay, so there's some correlation there between what you're doing, but the actual timings of it aren't as tightly correlated, and you might have to do some processing of your input data, some feature selection and feature extraction to understand where those correlations lie. Anyway, the suggestion for correlation was made. It's a good one. So here's an example. Sorry, this was real-world data, I should have said. This is collected from homes in Springfield, outside Ipswich, up near Brisbane, from Redback Technologies platform. Okay, so it's all geographically closely located. And here we have the voltage correlation heat map. So this is taking those series, and there's actually, in this case, we had about 50 of them, I think. Taking those series and looking element-wise at the correlations between them. Okay, so at each time slot, what's the correlations across them, and trying to work out if there's any patterns we can see there. Are there? Sort of. There's some blocks you can see appearing in there. Are there 3 blocks that you could think maybe are phases? Maybe. If you strain hard. Are you sure? Would you use this to do phase rebalancing? Remember, the goal here is to stop truck rolls. They cost about $2,000 each every time you send a truck out, right? At least, at a minimum. So you want to not have that happening. That's what your boss has tasked you to do. Save us money. Can you use this data to save your network company money? Maybe not. Maybe not when we look at it this way. Okay? So We will come back to this eventually. This is now the 12-hour average. Okay, we've taken the peak voltage over 12 hours rather than every 3 hours. It shows something slightly more revealing. I still wouldn't put too much money on it, but what I'm trying to show is that the way that you process the raw data affects how things might be clustered. Okay, so this is a simple sort of first thing you might try when you're doing clustering, to explore the data, get a feel for it, see if there is something there that you can use. So, unsupervised learning or clustering, clustering is the main class of unsupervised learning, has many different methods that you can use. What we've just seen there was an example of looking at correlation clustering, but there's quite a few other methods that you're probably very familiar with. Some of them are heuristics that are really quite effective, some of them are heuristics that can be quite misleading, and then there's, towards the bottom of that list, there's a few methods which are actually quite powerful and backed by solid maths and principled AI, we might say. So I'm just going to rush through the first few, and then we'll look at a couple of these in a little bit more detail, and then I'll give you an example of using a more sophisticated example. I'll just leave it at that for now. Okay, so hierarchical clustering or dendrograms are a way of arranging data into a tree that looks something like this, according to some sort of distance metric. So you start by putting data objects that are close together according to some metric that you've come up with, grouping them into pairwise clusters or small clusters, and then expanding the radius that you're looking in and making these clusters larger and larger until eventually you group all the data together. They can give you a good feel for the data, let you know if there's any clear-cut clusters or groupings that you should investigate. But they're quite susceptible to how you measure distance and how you measure your features. So you can get very different looking dendrograms coming out of this analysis depending on exactly how you set up your distance metrics and how you select your features. Okay. Another sort of better grounded approach and well used, and I'm sure you're all familiar with this, is Kmeans. Okay. So who hasn't seen Kmeans? Okay, so Kmeans is an iterative clustering algorithm. Here we have some unlabeled data to start with. This is the green data up here. Okay, and we're going to try and group that data into, in this case, 2 clusters. Okay, and Kmeans progresses iteratively. You start by guessing some cluster midpoints. In this case, the guesses are terrible, but it's instructive for seeing how the algorithm works. So you guess the midpoints, then you find the normal bisector between the 2 midpoints, and you regroup or recluster according to your partition from that bisector. Okay. Then you find the midpoints again. They've moved now, right, because they're based on the data. Again, apply the bisector. Find the midpoints again, apply the bisector. Doing this over and over again, eventually the algorithm converges. It always converges to a local optimum. So this cluster is not necessarily optimal by any sort of information metric, but K-means always converges. That's why it's quite useful. There are always local optima to these types of problems. They have penalty functions or similarity metrics which are bounded and finite, so they must have a maximum on the domain. So you will always get convergence. The problem is they're also irregular, so you may have more than one maximum of whatever penalty function you're trying to minimise. So there's more than one solution to this type of a problem. Okay, so K-means is pretty good. It's useful. Again, it's something that you can just apply out of the box. It always converges. It gives you a good idea of whether there are some clusters in there. One of the drawbacks of K-means is that you have to choose the number of clusters to start with. Sometimes it's easy, sometimes it's not easy. Okay. Now that approach, okay, you all know K-means, but the point of showing this to you is that, particularly for clustering, one of the underlying techniques for developing clusters isn't sort of process the data and get solutions or labels out. It's to use iterative methods, to refine, sort of to learn on as a process where the clusters are. And when we see some of the more sophisticated methods on the next couple of slides, you'll see that this idea of using iteration is kind of key to clustering. Okay, so something like Kmeans are Gaussian mixture models. All sorts of mixture models actually, but Gaussians are very easy to use. What we have here, circles representing, say, the first standard deviation of a multivariate, or in this case bivariate normal distribution. So we have two of these. They've been centered as an initialization at the same center points as the K-means algorithm. Okay. What we want to do is we want to adjust the means, the variance and covariance of these distributions so that they explain the clusters in the data with maximum log likelihood, or maximum log likelihood. So what you can think of these as being is, you know, the shape of a normal distribution. If you rotate that through 3 dimensions, you get a lump, basically. And the way this algorithm will progress is we're going to skew the covariance, which stretches the lump out, so you might get a longer lump in one direction, so it's more like an ellipsoid, and also rotate it and translate it. Okay. That sounds complicated, but it's actually quite easy if you don't try and do it all at once. You again use this iterative approach. So for Gaussian mixture models, we have those 3 parameters of the Gaussians that we're using that we're going to adjust. And within a sort of a Bayesian framework, we're also thinking about the posterior probabilities of a particular data point, so one of the dots there, being in one cluster or the other. Okay, so starting from here, we have these 2 midpoints. We have the lumps, which are overlapping sort of along the line of their bisector, which gives different probabilities of the data points here being in those 2 different clusters, being part of the mixture or a different part of the mixture. Okay. Oh, sorry, I should have said down here. We have the weight of the, I'll just explain those circles a little bit more. We have the weight of the, well, first of all, the multivariate normal distribution gives us the probability that X, a particular data point, is in cluster K, given the mean of that multivariate normal and the covariance matrix of the multivariate normal. Okay, so that's our conditional probability that X is in a particular cluster. Then the pi here is the weight applied to the cluster. So not all clusters are equal. They're created equal to start with, but as the algorithm progresses, we might put more weight on one or the other, depending on how many of the data points they explain. Okay, so we're going to iteratively update the weights of each cluster, and then on the other side of the iteration, we'll update the mean and covariance matrices. Okay. So back to here. In the second plot here, we have indicated by the shading of those data points, we have the posterior probability that each data point is either in one cluster or the other. So those which are closer to the red circle are more red, those that are closer to the blue circle are more blue, and those that are on that line separating the 2 are sort of a purpley colour, the mix of the blue and the red. Right, so that gives us then a way of adjusting the means and the covariance. So what we're going to do is we adjust the mean and the covariance of the normal distribution according to those posterior weights, those posterior probabilities. Okay, so if you're more likely to be in this cluster, then you have a greater effect on the recomputed mean and covariance. Okay, so we can see that this cluster is spread out. It's long and skinny. The red side is long and skinny. It's got a mean somewhere over here, and that's reflected in the adjustment to the mean and the covariance of that red circle. Similarly for the blue circle. Okay, now these 2 alternating steps are called the expectation step, that was what I just explained, and the maximization step, where you then find the maximum a priori probability that you're in one cluster or the other. Okay, so this expectation maximization algorithm is actually a general purpose algorithm for fitting mixtures of all sorts of different probability models. We work with Gaussians because recomputing these Gaussian normals is quite easy. Okay. Now this algorithm progresses again iteratively, so the next step we recompute the weights. You can see the shadings under here have changed. Some of these ones down here are more blue than they were red. Some of these up here are now more red than they were blue up in the corresponding plot here. We again adjust the means and the covariance matrices. We do this over and over again, and we end up with these probabilistic clusters. Okay, so at this point I want to bring in a distinction between something like Kmeans and Gaussian mixture models. In Kmeans, you're either in one cluster or you're not. In mixture models, there's a probability associated with you being in one cluster or in another cluster. Okay, so we call these hard clustering or soft clustering, or sometimes fuzzy clustering. I don't like that term. Probabilistic clustering is probably the better term to use. Okay, so this is a key distinction to be aware of. Sometimes we have hard clustering, sometimes we have soft clustering. Soft clustering, which gives you probabilities, is quite useful for when you're really unsure about what's going on. Hard clustering is usually quicker, a little bit dirtier, but it can give you an answer if that's what you need. We'll see the same distinction later when we look at classification, hard classification versus probabilistic classification. Okay, how am I going for time? Pretty good. Right, so I like Gaussian mixture models because they've got some more solid principles sitting behind them than something like Kmeans. You need to wrap your head around the theory regarding the way the expectation maximization algorithm works and what exactly the mixture of multivariate normals is doing. These also generalize up to more sophisticated Bayesian methods where you might embed this all in a Gaussian process. Okay, so some of you may have come across the term Gaussian processes. Another layer of difficulty on top of what's here. We'll see something similar to that in the example I'll talk about in the second session. And just to reiterate the point that we don't just have Gaussian mixture models, you can have all sorts of other mixture models. You can have the underlying distribution doesn't necessarily have to be Gaussian. Okay, it's just they're analytically tractable, so they're quite useful. Okay, this plot didn't quite come out as well as I'd hoped. But that's okay, we'll persevere. The next method that I'd just like to review for your information is called affinity propagation. I interrupted Anna on Tuesday when she was talking about belief propagation and the max product algorithm. Affinity propagation is another algorithm in that same class of algorithms. They all have a similar algebraic structure. If you look at them in terms of abstract algebras, they're all what are called C semirings or commutative semirings, which just means, so semirings are actually a very fancy word for saying you might have something like the real numbers and you're doing addition on the real numbers. Okay? They have an identity, which is 0. If you add 0 to anything, it doesn't change. And you need to have an idempotent element as well, which in the case of the real numbers is infinity. So if you have infinity plus the real numbers, applying infinity, either whether you're doing sum product or max sum, if you add infinity once, you don't need to add it again to get infinity again. That's idempotency. In this case, we have a min-max semiring. Again, it has the same underlying algebraic structure. But affinity propagation has a particular task in mind. It's given some data. What you want to do is you want to find an exemplar. Okay, your task is to find the data object in your set of data that best represents a particular cluster. So you're not looking for the median or you're not looking for just labels. Now you're looking for an exemplar. So you're looking for that particular, perhaps it's a customer or a representative feeder in your set of low voltage feeders that you're looking at, or there might be some exemplar that you're trying to pull out, okay? Which is a real world data point, not something you've made up. Again, affinity propagation is an iterative algorithm, and it has the same sort of scheme as before. You compute some metric of whether or not you're a good exemplar, and then you exchange values or you do another step which works out whether or not everyone agrees that you are a good exemplar. Okay, these two measures are called responsibility and availability. Okay, responsibility is how good everyone else thinks you are at being an exemplar for the group around you. And availability is whether or not you think someone else would make a good exemplar. Okay, so if you think of the data points, I'm going to go back a slide. So if we think of these data points here as forming a complete graph, so they're all connected to each other, they would then pass messages to each other saying, you're close to me, you're like me, you'd be a good exemplar, and receive messages in saying, hey, you're close to me, you'd be a good exemplar for a cluster that I'd be happy to be associated with. Or if you're a long way away, the value would be very small. Okay? And that's what these two steps here are, responsibility updates and availability updates. Okay. Now, it turns out that running this type of an algorithm allows you to automatically generate a set of exemplars for data that's unclustered. And you can do this without having to say how many exemplars you want. There's always some sort of a catch with these types of algorithms. In this case, the catch sits in determining the measures that sit in here, these S measures, which are the similarity metric. Okay, it's always the similarity metric that gets you. That's why I started asking the question at the start of the day, how do you work out whether two time series are like each other? Okay. But for the task of finding an exemplar, affinity propagation is probably one of your first go-tos. Okay? So now I'm going to get you to do something, because I've talked enough. So hopefully you've been emailed the materials for today. In there's some data and a Python script. And we're going to have a look at this voltage data. So for this part of the session, the Python packages you'll need will all have come with Anaconda, if you've installed the Anaconda distribution. If you didn't, you'll need matplot library and NumPy, pandas, and scikit-learn, okay, which are sort of standard things to have. And if there's any trouble, shout out. Okay, how are we going? So that data is not real-world data. I don't have permission to give you the real-world stuff. This is taken from some three-phase studies done by one of the PhD students I'm supervising who isn't sitting in the back row at the moment, unlike three of the others up there. So this is three-phase data that comes out of OpenDSS for a small network. So treat it with a grain of salt in that it's probably a lot cleaner than real-world data. But nonetheless, we have a low-voltage section of the network with a couple of spurs on it, some groups of houses that are, it's residential, it's a residential feeder, some groups of houses that are fairly closely located, some that are quite spread out along a long road. And the data is 1 hour resolution, voltage data for a year for 45 customers. And what we're going to do is apply labels or group the customers. Ah yes, you'll need the Seaborn package as well. So I forgot about that. That gives pretty plots. Prettier than just matplotlib. Anyone having any trouble accessing the data or anything like that? Things are running? Yeah? Not yet? Okay. Does anyone need any help? Okay, so we should have seen something like this up here. If you're using one of the IDEs, it's probably very small down in the corner. Okay, so people have this working. Some people are happy, some people are frustrated. So that's our target, right, to see that. If you then go and uncomment the code below that first block, we're going to apply a clustering method called spectral clustering. The method itself is in the class of spectral methods that Anna was looking at on Tuesday. She was talking about spectral clustering or spectral classification. Which was she doing? I can't remember now. There were eigenvalues and eigenvectors, so it was spectral, right? The idea is that either the singular value decomposition or some other linear algebra-based decomposition of the product of the input matrices and their transpose gives you a model or a measure of the connectedness of different data points with each other. Okay, and then you can exploit that to build up a network of like or similar data points. Okay, that's what correlation is, right? That's what correlation analysis is. This is an old idea. It's been around for a couple of hundred years. We're just getting better and better at refining it. And with the growth in computing power, we can do it for much larger data sets than ever before. Okay, so this is one of Gauss's ideas, really. Okay, so if you run the second part of the code using the spectral code clustering algorithm, what's happened is those data points which we saw before are now grouped and rearranged, right? So the X and Y labels have been rearranged into the clusters. Okay, the colours have changed as well. Does anyone see three phases in that? What else might we be discovering in this data? What might be confounding our analysis, causing us confusion?
Some separation of voltages within the phases themselves, I guess. It would essentially create more than three clusters.
Yep. Something even more fundamental as well. Well, consumer behaviour, yeah. There was some that's a good one, not in this data, but in some of the real-world data, we think we might be able to tell if people's houses face the north or on the wrong side of the hill or that sort of thing. Yeah, but not in this case. But it's good thinking.
The big thing that we've done with this, we do a bit of phase identification where we work, is we've got customers who would be on a phase with, say, like they're in a group of a phase. We've got, say, 10, 11 customers, and that one customer in particular is pulling a significant amount of load more. That combined with, say, a very slight degradation in their neutral service line, I guess, the voltage decrease relative to the current increase is much larger than everybody else, and that usually throws grouping algorithms into a bit of a disarray. It thinks, okay, there's actually now 4 or 5 clusters, not 3, and it's useless. So that's usually a telltale sign for us that something's wrong with that particular customer rather than the rest of that group.
Right, that's interesting to hear. Right, so you're using that for neutral fault?
Yes, so we've got a CPLEX algorithm running now to identify distinct groups, I guess, between customers on a distribution transformer.
Yep.
and most of the time it works. As in, like, it's a very good algorithm, and it works for, like, say, over 90% of the time. But then the little edge cases, I guess, throws it into disarray, and usually that gets clumped into, say, an unknown phase group, or it can't calculate, or something like that.
Yeah, great to hear.
Yeah,
very interesting.
So in the code, the number of clusters are 5.
Sorry, that's the maximum number.
Oh, okay. Thank
Good
you.
question. Yeah. So the other thing in this particular set of data that stands out is, and you don't know this because you haven't seen the network topology, but there's a few, it's quite a forked network. So there's some correlations with the voltages for the customers that are a long way away from the feeder head versus those that are close to the feeder head, or that are downstream of the fork. Okay, so that's one thing. But if we knew that, we could incorporate that in some way into the model as well. So the clustering data that I showed you earlier, all right, so this, the stuff that we started with, I kind of misrepresented what it was slightly. It's not actually the voltages or the correlations between the voltages. It's a physics-informed type model where we've taken into account the expected sag and surge in voltages given where customers are on the feeder. Okay, but that I'm not permitted to tell you the details of what's going on there. And I don't actually know. They haven't explained to me exactly what's going on. But at the Centre for Energy Data Innovation at UQ, there's a fellow named Richard Bean, who, if you're interested in this stuff, I suggest you get in contact with him.
Is that Mr. Bean?
It's Dr. Bean.
Oh, Dr. Bean.
I tried that one on him. He was not impressed. Okay, so did that sort of make sense to people? You could see how it was kind of working and why it, maybe explain a little bit why it wasn't working and where we need to apply more attention, where we can possibly exploit what we know about the network, and what, as was beautifully given as an example, what other confounding effects there might be to our clustering process. All right. So this is these are things that you use your expert knowledge to inform the machine learning about. Okay, machine learning algorithms. The machine bit is still quite stupid. It still requires you to apply what you know about the system. It won't just solve your problems for you. Okay, so it pays to think a lot before you just start throwing methods at problems like these. After the break, I'll just give you a heads up for what we're going to be doing. We're going to be doing some time series clustering. I'm going to throw you in the deep end because we're going to be looking at a hierarchical Bayesian methodology for clustering customers according to site information rather than the actual time series. So we'll go from heuristics like dendrograms all the way through to 3-layered hierarchical Bayesian models in the space of 2 hours. This will be more an explanation of how the methodology works and a particular class of mixture models called Dirichlet processes or Dirichlet mixture models, which are particularly useful for mixing over categories of data objects, where the underlying model can be anything. It can be almost anything, okay? This will hopefully be clear to you by the end of the next session. Okay, cheers.